Hi, I'm Nicholas Conlon. I'm a PhD student at the University of Colorado Boulder, and I will be discussing our paper titled Generalizing Competency Self-Assessment for Autonomous Vehicles using Deep Reinforcement Learning. As a motivation, human autonomy teams are and will be expected to accomplish complex tasks in high-risk and uncertain environments. Here, an operator may not be a robotic expert, but will need to establish a baseline understanding of an autonomous system's abilities in order to appropriately utilize and rely on the autonomous system. This reliance is what we refer to as trust. And misalignments of trust has been shown to lead to misuse, where the operator pushes the autonomous system beyond its limits, causing damage to the system or even mission failure, and disuse, where the operator may not utilize the autonomous system when they otherwise could have, wasting precious time and resources. Towards this goal of trust alignment, in this work, we build on previously developed techniques to enable agents to assess their self-confidence in the outcome of a task and communicate that information in a meaningful and intuitive way to an operator or teammate. As an example, consider the problem of a team conducting an ISR mission against an adversary airstrip with a small man-portable UAV, such as the MQ-7 Raven shown here on the right. The UAV is assigned to autonomously fly to an ISR collection zone, denoted with the blue circle in the image, as well as maintain a minimum altitude. The operator may not be technical and may have received minimal training prior to the deployment. There could be adverse weather conditions, such as high winds, and unknown to the operator, the autonomy is not rated for these conditions. The operator decides to go ahead with the mission, causing a misuse of the system and mission failure. So our core question is, for a given task, how can we align the operator's trust with the autonomous system's abilities? We first formulate this problem using deep model-based reinforcement learning. This allows the agent to learn a model of the world it operates in and use this model in a model predictive control framework to execute the task that we assign it. Once we have a trained model, we can use factorized machine self-confidence to assess our system. FAMSEC consists of 5 related factors which allow an agent to self-assess its ability to accomplish a given task. These factors include the agent's interpretation of the task, the quality of the model, and the quality of the solver planner that the agent is using, the agent's past experiences, and the agent's assessment on the outcome of the task. For this work, we'll be focusing on the agent's assessment of the task outcome, known as outcome assessment. Now, outcome assessment is computed by first sampling a set of simulation trajectories. Next, the agent builds a distribution of rewards based on those trajectories. Then an operator chooses a minimum acceptable reward threshold, which we call R star. Given R star and the reward distribution, the agent then computes the upper partial moment over the lower partial moment, which is the ratio of all rewards above R star to all rewards below R star, essentially a risk versus reward metric. Next, the UPM-LPM is transformed into the range of -1 to 1. And mapped to a semantic labeling scheme, which describes the agent's confidence in achieving rewards greater than R star. And the operator can vary R star based on their desired reward threshold. But this begs the question, how does a non-expert user choose a rewards-based threshold? Especially when rewards can change due to many factors, including retuning of the autonomy, the task, or other related factors. And these factors may not even have an effect on the overall task outcomes. We propose a generalized form of this rewards-based outcome assessment called Generalized Outcome Assessment. Here, as an outcome assessment, the autonomy begins by sampling a set of simulated trajectories. Now, instead of looking at rewards, the autonomy built a distribution of ranked equivalence classes of outcomes, where increasing rank indicates a more desirable outcome. For example, for our UAV ISR mission, we have 6 equivalence classes representing collection time outcomes in seconds. ranging from undesirable outcomes of 0 to 10 seconds to desirable outcomes where the UAV is collecting for almost the duration of the task. That would be 40 to 50 seconds. Now, based on their desired outcome, an operator can choose an acceptable outcome threshold, which we call Z star. And given Z star, the autonomy can then compute the UPM-LPM ratio, transform it, and map it into a semantic label. Now, this label indicates the agent's confidence in achieving a specific outcome better than or equal to the outcome desired by the operator. And the operator can vary Z star to their desired outcome of interest. And we believe that generalized outcome assessment offers a more intuitive way of understanding an agent's self-confidence in a task. Additionally, if there are multiple constraints or sub-goals in the task, the autonomy can compute the GOA assessment for each. For example, if the operator is interested in the time the UAV is collecting data and the time it is maintaining a minimum altitude, this can easily be accommodated. Now, returning to our autonomous UAV ISR mission. The task we are interested in is composed of two subtasks. First, the UAV must fly to and remain in the collection zone. Second, it must also maintain a minimum altitude between 100 and 200 meters. We will now analyze the UAV's self-assessment under GOA and OA for a sample of 60 trajectories, each of 60 seconds. Looking at traditional rewards-based outcome assessment first, the left plot shows the outcome assessment score and label associated with a specific reward value. However, we may not know, for example, what 9 times 10 to the 7th reward means. And the tune rewards may be more tied to the specific platform than the actual task. Here, it's not completely obvious how to make sense of these rewards with respect to the task. Moving on to generalized outcome assessment, here for maintaining altitude. We can clearly see there's a connection between the GOA score and the task performance. For example, we now know that the UAV has a very good confidence in maintaining altitude for just about the duration of the task. And now, moving to generalized outcome assessment for in-zone collections. Again, we can clearly see a connection between the GOA score and the task performance. We now know that the UAV has a very good confidence in 30 or more seconds in the zone, but very bad confidence of 50 or more seconds in the zone. With this information, an operator can appropriately choose to use or not use the autonomy. In summary, we formulated a UAV ISR mission as a model-based reinforcement learning problem and showed the value of our generalized outcome assessment approach over traditional rewards-based outcome assessments. Here, GOA is shown to be a more intuitive method to align operator expectations with predicted platform performance. Thank you.